How fast can humans really go in space? And what's the ultimate speed limit? It's a question that lies at the heart of our cosmic ambitions. Every rocket launch, every probe we send beyond Earth's atmosphere, is another attempt to find the answer. We've built machines that slice through the void faster than any jet, using the gravity of entire planets as slingshots to gain speed. And yet, when compared to the endless expanse of space, even our fastest creations are still moving at a crawl. So, if you want to know how fast we can truly travel through the cosmos, and what might one day take us beyond our limits, watch this video till the end and subscribe to the channel. Let's begin. Speed in space isn't just about bragging rights. It's about survival, discovery, and the future of our species. The vastness of space is almost impossible to comprehend. The distances between planets aren't measured in miles we can drive, or even in flight hours. They're measured in millions and billions of kilometers. Traveling from Earth to Mars, for instance, takes around 6 to 9 months with current rocket technology, depending on the planet's alignment. A trip to Jupiter could take several years, and if we aimed for the nearest star system, Alpha Centauri, it would take more than 70,000 years with our fastest existing spacecraft. That's longer than all of recorded human history. This is why speed matters so profoundly in space travel. Faster propulsion means shorter missions, reduced exposure to radiation, and a much higher chance of human survival on long journeys. The difference between months and weeks, or between centuries and decades, could determine whether space colonization remains science fiction or becomes a new chapter in our evolution. Faster spacecraft could make Mars not just reachable, but livable, with steady supply routes and frequent transport. It could also unlock the outer solar system for human exploration, sending astronauts to moons like Europa or Titan, where oceans may hide beneath the ice, waiting to tell us if life exists elsewhere. The faster we can move, the more realistic these possibilities become. It's not just about shaving time off a trip, it's about expanding what's possible for civilization. A spacecraft that can reach Mars in weeks instead of months would mean easier resupply, safer missions, and perhaps even regular travel between worlds. In short, speed is the bridge between exploration and colonization, between dreaming about the stars and actually living among them. When we talk about speed in space, it's not as straightforward as it sounds, because in the cosmic arena, motion is always relative. Unlike driving on Earth, where speed is measured against the ground beneath your wheels, in space, there's no fixed frame of reference. Every planet, moon, and spacecraft is constantly moving, spinning, and orbiting something else. So when scientists describe a spacecraft's speed, they have to specify relative to what? The Earth, the Sun, or even the Milky Way itself. Let's start with the basics. There's orbital velocity, the speed needed to stay in orbit around a planet without falling back down or flying away. Around Earth, that's about 28,000 kilometers per hour, 17,500 miles per hour. The speed astronauts aboard the International Space Station travel at as they circle our planet every 90 minutes. Then there's escape velocity, the speed required to completely break free from a planet's gravitational pull. For Earth, that magic number is around 40,000 kilometers per hour, 25,000 miles per hour. Anything slower, and gravity drags you back. Anything faster, and you're off into interplanetary space. But once you've escaped Earth's gravity, things get more complex. You then talk about interplanetary speed, how fast a spacecraft moves relative to the Sun or other celestial bodies. For instance, when a probe travels to Mars, its speed relative to Earth changes constantly as both planets move along their orbits. What might seem slow from one perspective could be lightning fast from another. The Parker Solar Probe, for example, holds the record for the fastest human-made object, moving over 700,000 kilometers per hour relative to the Sun. Yet, from Earth's point of view, that number would be slightly different, because Earth itself is racing around the Sun at about 107,000 kilometers per hour. So when we ask, how fast can we travel in space right now? We're really asking, how fast are we moving relative to what? The answer shifts depending on the frame of reference, but the principle remains the same. In a universe where everything is in motion, speed is always a matter of perspective. When it comes to the fastest speeds ever achieved by human beings, one mission still reigns supreme, a feat from more than half a century ago that remains unmatched to this day. The Apollo missions, the crown jewels of human space exploration, didn't just land astronauts on the moon, they also turned those astronauts into the fastest humans in history. During Apollo 10, the crew reached a blistering 39,897 kilometers per hour, 24,791 miles per hour, relative to Earth during their re-entry from lunar orbit in May 1969. That number isn't just impressive, it's a reminder of how extraordinary the engineering of that era truly was. Even with today's advanced technology, no human has traveled faster than those Apollo astronauts did more than 50 years ago. To understand why this record still stands, we have to look at what made those missions so unique. The Apollo spacecraft didn't just orbit Earth, they left its gravitational influence entirely. To return from the Moon, the astronauts had to perform a translunar injection burn, a precise maneuver that allowed the spacecraft to fall back toward Earth's gravity well at tremendous speed. Essentially, they used both the pull of Earth's gravity and the motion of their lunar orbit to accelerate naturally, gaining enormous velocity as they approached home. By the time they hit the upper atmosphere, they were moving faster than any human-made object carrying people ever had. This staggering speed came with extreme danger. Re-entry from lunar return wasn't just about slowing down, it was about surviving the process. The Apollo command module had to endure temperatures exceeding 2,700 degrees Celsius, nearly 5,000 degrees Fahrenheit, as it slammed into the atmosphere. A small miscalculation in the angle of re-entry could have spelled disaster. Too shallow, and the capsule would skip off the atmosphere like a stone on water. Too steep, and it would burn up instantly. Yet, thanks to meticulous engineering and careful planning, every Apollo crew that made the trip from lunar orbit to Earth returned safely, a testament to the brilliance of the scientists and engineers who designed the mission. The reason that speed record still stands has a lot to do with the simple fact that no human has gone beyond low Earth orbit since Apollo 17 in 1972. Every crewed mission since then, from the Space Shuttle program to the International Space Station, has stayed relatively close to home, orbiting Earth at around 28,000 kilometers per hour, 17,500 miles per hour. While that's fast enough to circle the planet every 90 minutes, it's nowhere near the velocity needed to break free from Earth's gravity, let alone achieve lunar return speeds. We've built spacecraft that can go much faster, probes like Voyager, New Horizons, and the Parker Solar Probe, but they've all been uncrewed. Part of the reason for that is safety. The speeds required to reach or return from the Moon or beyond expose astronauts to enormous risks, high radiation levels, extreme re-entry forces, and the possibility of catastrophic failure if something goes wrong even slightly. For crewed missions, the margin of error must be near zero. The Apollo astronauts accepted those risks in a period of intense competition and national pride, the height of the space race. But modern missions tend to prioritize reliability and sustainability over raw speed. There's also the issue of technology and purpose. The Apollo missions were designed specifically for deep space travel using the powerful Saturn V rocket, which remains the most potent rocket ever successfully flown. Standing over 110 meters tall, it could deliver more than 34 million newtons, 7.6 million pounds, of thrust at launch, capable of propelling astronauts beyond Earth's orbit and toward the Moon. No rocket since then has surpassed the Saturn V's combination of payload capacity and energy output for human missions. Though NASA's new Space Launch System, SLS, and SpaceX's Starship are finally beginning to reach similar capabilities. Until humans return to the Moon or venture beyond, there simply hasn't been an opportunity to break that incredible record. But beyond the numbers and technology, there's something deeply symbolic about that Apollo speed record. It represents the pinnacle of human daring, the willingness to push against the boundaries of what was thought possible. The astronauts who flew those missions weren't just passengers. They were explorers traveling at velocities where even small mistakes could prove fatal. They experienced firsthand what it means to race through space, watching the stars blur slightly as they fell toward home, trusting their heat shield and their training to carry them safely back to Earth. And perhaps the most astonishing part is that the record wasn't broken by Apollo 11, the first moon landing, but by Apollo 10, the mission that served as a dress rehearsal for that historic step. The Apollo 10 crew, Thomas Stafford, John Young, and Eugene Cernan, came within 15 kilometers of the lunar surface, testing every maneuver except the final descent. Their re-entry speed set the record for the fastest humans in history, one that has endured across generations of space travel. As humanity prepares to return to the Moon through NASA's Artemis program, this half-century-old milestone may finally be challenged. Artemis missions will send astronauts not only back to lunar orbit, but eventually to Mars, where re-entry speeds could exceed those of Apollo. But until that day comes, the title of fastest humans ever still belongs to three brave men who, in 1969, rode a small metal capsule through the void at nearly 40,000 kilometers per hour, faster than any living being has ever gone. The story of Apollo's unmatched speed is a reminder that humanity has already proven we can go fast, breathtakingly fast, when the will, technology, and courage align. Yet, it also marks the beginning of a question that still drives us forward. If we could go that fast half a century ago, just how fast might we go next? If the Apollo missions made humans the fastest living travelers in history, then the Parker Solar Probe made our machines the fastest objects humanity has ever built. Launched by NASA in August 2018, the Parker Solar Probe was designed to do something both astonishing and dangerous: to touch the Sun. Its mission is to study the solar corona, the outermost layer of our star's atmosphere, where temperatures soar to millions of degrees Celsius. To get close enough to gather that data, Parker must dive deeper into the Sun's gravitational well than any spacecraft before it, and in doing so, it has shattered every previous speed record ever achieved by a human-made object. At its peak velocity, Parker Solar Probe is expected to reach speeds of over 700,000 kilometers per hour, about 430,000 miles per hour, relative to the Sun. To put that into perspective, that's fast enough to travel from Los Angeles to Tokyo in just 1 minute, or to circle Earth nearly 18 times in a single hour. At that speed, it's moving roughly 0.064% of the speed of light, an incredibly small fraction by relativistic standards, but unimaginably fast compared to anything else we've ever built. So, how does Parker achieve such jaw-dropping velocity? The answer lies in one of the most elegant tricks in orbital mechanics: gravity assists. Instead of constantly firing powerful engines, Parker uses the gravity of Venus, not to slow down, but paradoxically, to speed up. In spaceflight, gravity assists, also called slingshot maneuvers, involve flying close to a planet and using its gravity to alter a spacecraft's trajectory and velocity. For most interplanetary missions, this technique is used to gain energy and fling a spacecraft outward. But Parker's mission is different. It's actually falling toward the Sun, and Venus is being used to steal away angular momentum from its orbit, allowing it to spiral closer to the Sun's blazing surface. Each of Parker's close passes to Venus acts like a cosmic handbrake, dropping it into a lower orbit where the Sun's gravity accelerates it to extreme speeds. The closer it gets, the faster it falls. This interplay between gravitational pull and orbital mechanics is what allows Parker to achieve its record-breaking pace. No chemical rocket or sustained engine burn could ever supply the energy required to reach such velocity on its own. By the end of its mission in the late 2020s, Parker will have completed 7 Venus flybys, each tightening its orbit until it grazes just 6.16 million kilometers, 3.83 million miles from the Sun's surface. That's closer than Mercury's orbit. What's truly astonishing is how the spacecraft survives such brutal conditions. At those distances, sunlight is about 475 times more intense than it is on Earth. Temperatures soar beyond 1,300 degrees Celsius, 2,400 degrees Fahrenheit. Yet Parker's sensitive instruments are kept cool by an advanced carbon composite heat shield, only 11.5 centimeters thick. The probe systems are tucked behind this shield, maintaining an internal temperature close to room temperature, even as it faces a star that could melt metal in seconds. Every time Parker swings through its perihelion, the point in its orbit closest to the Sun, it not only sets a new speed record, but also becomes humanity's closest encounter with our parent star. What makes Parker's journey so poetic is that despite its blazing velocity, it's technically falling. It's not firing massive engines or riding an explosion like a rocket. It's obeying gravity in the purest form. The same force that keeps the planets orbiting the Sun is the same one that's pulling Parker to unimaginable speeds. Its velocity isn't powered by fuel, it's powered by physics itself. To put Parker's achievement into a broader context, consider this. The fastest crewed spacecraft ever, the Apollo Command Module, reached around 39,897 kilometers per hour, while even legendary missions like Voyager 1, which has been traveling through space since 1977, moves at only 61,000 kilometers per hour, 38,000 miles per hour, relative to the Sun. That means Parker is traveling more than 10 times faster than Voyager 1, and more than 17 times faster than the Apollo astronauts. It's the closest thing we've ever built to a solar bullet, hurtling through space so fast that a single grain of dust could destroy it if it weren't for its reinforced design and ultra-precise trajectory planning. But Parker's speed isn't just a record for the sake of pride. It's essential to its scientific purpose. By moving at these extraordinary velocities, the probe can plunge through the Sun's outer atmosphere before solar radiation and particle storms have time to cause catastrophic damage. Each pass brings new data about solar winds, magnetic fields, and energetic particles, helping scientists understand the complex forces that drive solar flares and coronal mass ejections, phenomena that can disrupt satellites, power grids, and communications on Earth. Parker's mission is, in many ways, the perfect example of how speed in space can serve science. The faster it travels, the deeper it can dive into the unknown. It's a technological marvel that blends raw physics with human ingenuity. A spacecraft that uses the gravity of a planet to hurl itself into the furnace of a star, surviving conditions no machine ever has before. The Parker Solar Probe reminds us that even though no human has yet traveled beyond the Moon in over half a century, our machines continue to explore where we cannot. They move faster, dive deeper, and endure more than flesh ever could, extending our reach farther into the universe with every mission. And as we continue to perfect the art of harnessing gravity, energy, and propulsion, the speed records Parker sets today might one day be the benchmarks for the next generation of star-bound explorers. It's a thrilling thought, a human-made object, not just orbiting a distant planet, but literally touching the atmosphere of a star, and doing it at hundreds of thousands of kilometers per hour. Parker Solar Probe is not just our fastest spacecraft. It's a symbol of how far humanity has come in understanding and mastering motion itself. For all our technological brilliance and cosmic ambition, there's a simple, frustrating truth about space travel. Going faster isn't easy. In fact, every extra kilometer per hour of speed comes at an enormous cost in energy. The reason we can't just go faster is rooted in one of the most fundamental laws of physics, the conservation of momentum, and in the harsh reality of rocket science. It takes an extraordinary amount of fuel to accelerate even a small spacecraft, and the faster you want to go, the harder it becomes. When we talk about spacecraft velocity, what we're really talking about is how much energy it takes to achieve that motion. To increase speed in space, a spacecraft must fire its engines and expel mass, fuel, in the opposite direction. This is the core principle behind Newton's third law. For every action, there is an equal and opposite reaction. The problem is that as you burn fuel to accelerate, you make the spacecraft lighter, which helps. But you also need to carry that fuel from the start, which adds mass. And the more fuel you add, the heavier the rocket becomes, meaning you need even more fuel to push that fuel. This creates a vicious cycle known as the tyranny of the rocket equation. The rocket equation, developed by Konstantin Tsiolkovsky in the early 20th century, mathematically describes this relationship. It tells us that the change in velocity, delta V, a rocket can achieve depends on two main factors: the effective exhaust velocity, how fast fuel can be expelled from the rocket engine, and the mass ratio, how much the rocket weighs fully fueled compared to when it's empty. What this means in practice is that if you want to double your speed, you can't just double your fuel. You might need 10 times more. The returns diminish rapidly. Most rockets today use chemical propulsion, which relies on the combustion of fuel and oxidizer to produce hot gases expelled at high velocity. While these engines are incredibly powerful, capable of launching hundreds of tons of metal and humans into orbit, they are also astonishingly inefficient in the context of interplanetary travel. The typical exhaust velocity of chemical rockets is only a few kilometers per second. Once you leave Earth's atmosphere, these engines become less practical for long-term acceleration. They're designed to give a short, powerful push, not a continuous one. That's why, after a spacecraft leaves Earth's gravity well, it mostly coasts. Once in the frictionless vacuum of space, no air resists its motion, so it doesn't need to burn fuel to keep moving. It just glides along at a steady speed. To go faster, though, it would have to burn more fuel, and every drop of that fuel had to be lifted off Earth first. Lifting fuel into orbit is extraordinarily expensive. For every kilogram of payload that reaches space, dozens of kilograms of propellant are burned just to escape Earth's gravity. This is the energy problem in its purest form, an endless battle between mass, energy, and efficiency. To understand how extreme this limitation is, consider this. The Saturn V rocket, which launched the Apollo missions, weighed about 2.8 million kilograms at liftoff. Yet, of that, only around 45,000 kilograms, less than 2%, actually made it into lunar orbit. The rest was fuel. That means nearly 98% of the rocket's mass was expended just to get the small command module and lunar lander to where they needed to be. And even with all that, the Apollo spacecraft topped out at around 40,000 kilometers per hour, a tremendous speed by human standards, but microscopic compared to cosmic scales. Now imagine what it would take to go 10 times faster, or 100. The energy requirement doesn't scale linearly, it scales exponentially. Kinetic energy increases with the square of velocity, which means doubling your speed requires 4 times the energy, and tripling it demands 9 times as much. To reach even 1% of the speed of light, about 3,000 kilometers per second, A chemical rocket would need an absurd, practically impossible, amount of fuel. The rocket would have to be larger than the entire visible universe, figuratively speaking, just to hold enough propellant to accelerate to that speed. There's also the issue of thrust-to-weight ratio. Chemical rockets are excellent for generating enormous thrust over short durations, perfect for takeoff from a planet's surface. But their efficiency, measured as specific impulse, is relatively low. Even the best chemical engines, like the Space Shuttle main engine, SSME, or the Raptor engines on SpaceX's Starship, have a specific impulse of about 450 seconds at best. In contrast, electric or ion propulsion systems, which we'll discuss later, can reach over 10,000 seconds, far more efficient, but far less powerful in terms of immediate thrust. Energy limitations also shape the design and destination of missions. Every planetary mission must perform a careful dance between available fuel, gravitational assists, and orbital mechanics to minimize the required energy. For example, instead of flying straight to Jupiter, a spacecraft might first orbit Venus or Earth multiple times to gain speed for free through gravitational slingshots. This saves fuel but takes years of travel time, a necessary trade-off given our propulsion limits. And then there's the raw economics of energy. Launching just 1 kilogram of material into orbit costs thousands of dollars. Increasing the speed of a spacecraft once it's already there costs even more energy, often requiring additional stages, boosters, or complex orbital maneuvers. That's why most space missions don't aim for fastest possible. They aim for fast enough to get there safely. It's a delicate balance between ambition and practicality, between what physics allows and what our current technology can deliver. Ultimately, our inability to go faster isn't due to a lack of imagination. It's a matter of physics and engineering limits. Every rocket, no matter how advanced, is bound by the same fundamental truth. The more speed you want, the more energy you must invest, and that energy has to come from somewhere. Until we develop propulsion systems that can deliver high efficiency and high thrust without carrying massive fuel reserves, our journeys through the cosmos will remain slow, steady, and governed by patience. This is the great paradox of modern spaceflight. We can escape our planet, orbit the Earth, and even reach other worlds. But when it comes to truly crossing the vast oceans of interstellar space, we're still crawling at a snail's pace compared to the speed of light. Yet, as history has shown, every technological barrier is temporary. And in the next step of our journey, humanity is already experimenting with new ideas that could one day break free from the limits of chemical propulsion altogether. At the core of nearly every rocket humanity has ever launched lies one simple principle: the conversion of chemical energy into motion. Chemical rockets are the workhorses of space travel, and despite all our advancements, this technology still forms the foundation of how we escape Earth's gravity. The idea seems almost primitive compared to the vastness of space. Take fuel and an oxidizer, set them on fire in a controlled explosion, and hurl the resulting exhaust out of the back of the rocket at incredible speeds. Yet, this process, violent, elegant, and astonishingly effective, remains one of the most powerful ways we know to generate thrust in the vacuum of space. To understand how chemical propulsion works, imagine a sealed chamber where a chemical reaction between a fuel and an oxidizer takes place. The fuel might be something like liquid hydrogen, RP1 kerosene, or hydrazine, while the oxidizer could be liquid oxygen or nitrogen tetroxide. When they combine and ignite, they produce superheated gases that expand rapidly, forcing their way out through a nozzle at high velocity. The escaping gases generate thrust, pushing the rocket forward according to Newton's third law of motion. For every action, there's an equal and opposite reaction. The effectiveness of this system depends on how efficiently the rocket can convert chemical energy into kinetic energy. In practical terms, this is measured by specific impulse, ISP, a metric that tells us how much thrust a rocket engine produces per unit of propellant consumed per second. The higher the specific impulse, the more efficient the engine. Typical chemical rockets, depending on their type, achieve an ISP between 250 and 450 seconds. For instance, the F-1 engines on the Saturn V rocket, which powered Apollo astronauts to the Moon, had a specific impulse of around 263 seconds at sea level. The Space Shuttle main engines, SSMEs, were much more efficient, reaching about 453 seconds in a vacuum. The beauty of chemical propulsion lies in its immense thrust. When you're trying to lift thousands of tons of payload off Earth, fighting gravity, drag, and atmospheric pressure, you need brute force. Chemical rockets provide it in abundance. The Saturn V produced 34 million newtons of thrust at liftoff. SpaceX's Starship, when fully operational, will generate even more, around 75 million newtons. These titanic forces are what make it possible to overcome Earth's gravitational pull and achieve escape velocity, the critical speed of roughly 11.2 kilometers per second, about 40,000 kilometers per hour, needed to break free from Earth's grasp. However, once a rocket escapes the atmosphere and enters the frictionless expanse of space, the very advantages that make chemical propulsion so powerful on launch become its greatest weaknesses. Chemical reactions burn fuel extremely quickly, and while they provide tremendous bursts of acceleration, they cannot sustain it for long periods. The fuel tanks that feed those engines are massive, and once they're empty, the rocket is left with little or no means to continue accelerating. This is why spacecraft like Apollo, Voyager, or Parker Solar Probe rely on short burns followed by coasting phases, using the momentum gained from those burns to carry them through space. The efficiency problem is what limits chemical rockets from being practical for interplanetary or interstellar travel. To reach Mars, for example, a spacecraft must accelerate for only a small portion of its journey. The rest is a long, slow drift through space. If you tried to use chemical propulsion to accelerate continuously, the amount of fuel required would grow exponentially, quickly becoming unmanageable. Even a modest increase in travel time reduction, say from 9 months to 3, would require an absurd amount of propellant. There's simply no way to carry that much fuel without the rocket becoming too heavy to launch in the first place. Another major limitation is energy density, the amount of energy stored in a given mass of fuel. Chemical propellants, while powerful, are relatively poor in energy density compared to what future technologies might offer. The combustion of hydrogen and oxygen releases a tremendous amount of energy per kilogram compared to most terrestrial fuels, but it's still minuscule when compared to nuclear reactions or even advanced electric propulsion systems. For perspective, the energy density of chemical fuel is measured in megajoules per kilogram, while nuclear fuels can reach billions of megajoules per kilogram. That's a difference of several orders of magnitude, a glimpse at why our rockets, despite their fiery grandeur, are still crawling in cosmic terms. The structure of a chemical rocket is also dominated by this inefficiency. Most of a rocket's mass at launch is propellant, not payload. The Saturn V, again, is the perfect example. Of its 2.8 million kilograms at liftoff, only about 5% reached orbit, and just a tiny fraction of that continued onto the Moon. The rest was fuel burned in a matter of minutes. Modern rockets have improved on this, but the ratio remains steeply tilted toward propellant mass. This means that while chemical propulsion is excellent for climbing out of deep gravity wells like Earth's, it's not sustainable for continuous acceleration once in space. Another issue comes from heat and mechanical stress. Combustion at thousands of degrees Celsius and pressures of hundreds of atmospheres places enormous strain on engine components. To manage this, rocket engines require intricate cooling systems, often using the propellant itself to absorb heat before combustion, a technique known as regenerative cooling. This adds complexity, cost, and risk to every mission. Even small imperfections can lead to catastrophic failures, as history has shown in numerous rocket accidents. Yet, despite all these limitations, chemical rockets are still our primary ticket to the stars, because they work. They've carried humans to the moon, delivered rovers to Mars, and launched telescopes that peer deep into the universe. They remain the only technology we have that can produce the kind of thrust needed to escape planetary surfaces. Every modern spacecraft, no matter how advanced its propulsion once in space, still depends on chemical rockets for launch. In essence, chemical propulsion is our first gear in the cosmic journey, powerful, explosive, and indispensable, but not built for cruising the interplanetary highways. It's the technology that gets us off the ground and gives us our initial push into the void, after which other, more efficient systems must take over if we hope to go farther and faster. As we look toward the future, humanity's next great challenge is finding ways to move beyond this fiery, fuel-hungry method of travel. We need engines that can accelerate continuously for months or even years without carrying mountains of propellant. Systems that convert energy more efficiently and sustain thrust over long distances. And that's exactly where our story heads next. The realm of ion propulsion and electric thrusters, where speed is gained not through brute force, but through precision, patience, and persistence. If chemical rockets are the brute force champions of space travel, muscles forged in fire and pressure, then ion propulsion systems are the elegant marathoners of the cosmos. They don't roar or explode, they whisper. They don't burn bright plumes of flame. Instead, they quietly push spacecraft forward, atom by atom, in a dance of precision and patience. And though they start slow, agonizingly slow, given enough time, these engines can achieve speeds chemical rockets could never dream of sustaining. At the heart of this technology is a profound shift in how we think about propulsion. Traditional rockets rely on chemical reactions to create explosive bursts of thrust, consuming vast quantities of fuel in seconds. Ion propulsion, by contrast, uses electricity, often generated by solar panels or nuclear power, to accelerate charged particles, ions, to incredible velocities. While the thrust produced is minuscule compared to that of a chemical rocket, the efficiency is extraordinary. Over time, these small, continuous pushes accumulate into breathtaking speeds. So how does an ion drive actually work? The principle is deceptively simple. A gas, typically xenon, is fed into a chamber where it's bombarded with electrons, stripping atoms of their electrons and creating a plasma, a soup of charged particles. These positively charged ions are then accelerated out of the engine by powerful electric fields, often created using grids charged to thousands of volts. As the ions are expelled out of the thruster at speeds up to 40 kilometers per second, the spacecraft is pushed gently in the opposite direction. The resulting thrust is astonishingly small, about the weight of a single sheet of paper pressing against your hand. But in the vacuum of space, where there's no drag or resistance, that constant, unyielding push builds up velocity over weeks, months, or even years. It's like a drop of water falling on stone, small at first, but unstoppable over time. The most famous example of ion propulsion in action is NASA's Dawn spacecraft, launched in 2007. Dawn's mission was ambitious, to visit not one, but two separate celestial bodies in the asteroid belt, Vesta and Ceres. Using ion propulsion, Dawn accomplished what would have been impossible for chemical rockets. Over its 11-year journey, the spacecraft changed its velocity by more than 41,000 kilometers per hour about 25,000 miles per hour, more than any spacecraft before it, while using less than 450 kilograms of xenon propellant. That's about the weight of a grand piano. To put that into perspective, if Dawn had used chemical propulsion, it would have needed tens of thousands of kilograms of fuel, an impractical amount for any launch vehicle. Yet, with its 3 N-star ion thrusters, Dawn quietly maneuvered through the solar system, gracefully adjusting its orbit and trajectory with precision unmatched by any chemical engine. It became the first spacecraft ever to orbit 2 extraterrestrial bodies, proving that slow and steady truly can win the cosmic race. Ion drives have also powered other groundbreaking missions. NASA's Deep Space One, launched in 1998, was the first to test ion propulsion in deep space, using it to fly by the asteroid Braille and the comet Borrelly. The European Space Agency's Smart 1 used an ion engine to travel from Earth to lunar orbit, marking Europe's first lunar mission. And in recent years, ion propulsion has found a place in commercial and defense satellites, helping them maintain stable orbits or reposition with remarkable fuel efficiency. The key advantage of ion propulsion lies in its specific impulse, which can reach values between 3,000 and 10,000 seconds, several times higher than the best chemical rockets. This means ion engines use fuel far more efficiently, producing more thrust per unit of propellant mass. For long-duration missions, that efficiency is priceless. A spacecraft equipped with ion propulsion can carry much smaller fuel reserves, freeing up weight for instruments, shielding, or cargo. However, this elegance comes at a cost, namely thrust power. Even the most advanced ion engines produce only fractions of a newton of force, making them unsuitable for launch or rapid acceleration. They can't lift off from Earth's surface or escape a deep gravity well. Instead, they are designed for the quiet emptiness of interplanetary space, where their slow but steady acceleration can gradually build up to enormous speeds. For example, after years of continuous thrusting, an ion-powered probe could reach speeds exceeding 150,000 kilometers per hour, 93,000 miles per hour, faster than any crewed spacecraft and rivaling the velocity of some of the fastest uncrewed probes. Another critical factor is power generation. Ion thrusters need electricity, a lot of it, to ionize gas and accelerate particles. Most spacecraft use solar panels to provide this energy, but as they move farther from the sun, power becomes scarce. That's why future deep space missions may rely on nuclear power sources, such as radioisotope thermoelectric generators, RTGs, or fission reactors, to keep the thrusters running far from sunlight. One of the most exciting future prospects is NASA's planned Psyche mission, set to explore the metallic asteroid 16 Psyche. It will use Hall effect thrusters, a type of ion engine that traps electrons in a magnetic field to increase ionization efficiency. This propulsion system offers a glimpse of the future, quiet, efficient, and capable of operating for years without refueling. Beyond NASA, private companies and research agencies are also investing in electric propulsion. SpaceX, for instance, uses ion thrusters on its Starlink satellites for orbital adjustments, while Northrop Grumman and Boeing have developed advanced electric propulsion modules for commercial spacecraft. As these systems improve, we may one day see human missions equipped with hybrid propulsion, chemical rockets for launch, ion drives for the long cruise through interplanetary space. What makes ion propulsion so revolutionary is its philosophical shift. For centuries, we've thought of travel in terms of brute power. Faster meant burning more fuel. Ion propulsion flips that idea on its head. It's not about speed through force, but speed through endurance. It's the technology that could one day take us to the outer planets economically, or even on the first robotic missions to nearby stars. And while ion drives are still too weak to propel crewed ships across vast distances quickly, they represent a crucial step towards sustainable and scalable spaceflight. They remind us that in the grand expanse of the cosmos, patience can be the greatest form of power. The next frontier takes that patience one step further, using not electricity, but light itself. If ion propulsion is the whisper of the future, then solar sails are the silent gliders, harnessing the radiation of the sun to drift eternally through space without a drop of fuel. Among all the methods humanity has imagined to traverse the stars, solar sails stand out as perhaps the most poetic. Spacecraft that don't burn fuel, don't roar with engines, and don't rely on any chemical reaction at all, but instead glide through the cosmic sea powered purely by sunlight. The idea sounds like something out of science fiction, but it's based on solid physics. Just as wind pushes a sailboat across the ocean, light, even though it has no mass, can push a spacecraft across the solar system and, one day, perhaps to the stars themselves. The concept of solar sailing dates back over a century, first proposed by Russian scientist Konstantin Tsiolkovsky, and later refined by others like Friedrich Zander in the early 20th century. The principle relies on radiation pressure, a subtle but continuous force exerted by photons, particles of light, when they strike a reflective surface. While photons have no mass, they carry momentum, and when they bounce off a mirror-like sail, they transfer a tiny amount of that momentum to the surface. The effect is minuscule. Each photon's push is almost imperceptible. But in the vacuum of space, with no friction or drag, that tiny nudge builds up over time into continuous acceleration. A solar sail is essentially a large, ultra-thin, reflective sheet, usually made of materials like mylar or kapton, stretched over lightweight supports. These sails can be enormous, hundreds of square meters in area, yet only micrometers thick. Their job is simple: to catch sunlight and convert it into motion. The larger and more reflective the sail, the greater the force it can harness from sunlight. Near Earth, the pressure exerted by sunlight is only about 9 micronewtons per square meter, roughly the weight of a few grains of sand. But as a sail spans hundreds or thousands of square meters, the cumulative force becomes meaningful. Unlike chemical or ion propulsion, which rely on limited stores of fuel, solar sails are propellant-free. As long as there's light, from the sun or another star, a solar sail can keep accelerating indefinitely. Theoretically, this means a solar sail could reach speeds of tens or even hundreds of thousands of kilometers per hour, given enough time. It won't win any races off the launch pad, but over months or years, it can surpass any conventional rocket. This elegant form of propulsion moved from theory to practice in the early 21st century. One of the pioneering missions was the IKAROS, interplanetary kitecraft accelerated by radiation of the sun, launched by the Japan Aerospace Exploration Agency, JAXA, in 2010. Icaros became the first spacecraft to successfully demonstrate solar sailing in interplanetary space, deploying a 14-meter wide sail made of ultra-thin polyimide film. Using sunlight alone, Icaros accelerated gradually and proved that radiation pressure could indeed be used for navigation and control, even across millions of kilometers. A few years later, the Planetary Society, a non-profit founded by Carl Sagan, Bruce Murray, and Louis Friedman, launched LightSail 2, a crowd-funded spacecraft that captivated the world in 2019. About the size of a loaf of bread before deployment, LightSail 2 unfurled a 32 square meter reflective sail in Earth orbit. Over time, it raised its apogee, the farthest point in its orbit, purely by harnessing sunlight. No fuel, no thrusters. It was the first time a spacecraft in Earth orbit successfully used solar sailing to change its trajectory, marking a turning point for space propulsion. LightSail 2 proved that the dream works, that light itself can be a viable form of thrust. Though its acceleration was tiny, only a fraction of a millimeter per second squared, its success was symbolic of something much larger. A future where spacecraft could journey through the solar system without ever running out of fuel. The Planetary Society's mission demonstrated that with large enough sails and patient engineering, humanity could one day send fleets of silent, gleaming craft across the cosmos, powered by nothing more than starlight. But solar sailing's most exciting vision goes far beyond our solar system. Enter Breakthrough Starshot, a project backed by billionaire Yuri Milner, physicist Stephen Hawking before his passing, and a team of world-class scientists. Their audacious goal? To send a fleet of tiny gram-scale spacecraft, known as starships, to the nearest star system, Alpha Centauri, just over 4.37 light-years away. Here's where the concept becomes truly mind-bending. Instead of relying solely on sunlight, Breakthrough Starshot plans to use ground-based lasers, a colossal array of synchronized beams, to blast an ultralight sail to near-relativistic speeds. The target speed, up to 20% of the speed of light, or roughly 60,000 kilometers per second. At that velocity, these miniature probes could reach Alpha Centauri in just over 20 years, making interstellar travel, at least for robotic explorers, possible within a human lifetime. To achieve this, each light sail would be incredibly small and thin, perhaps just a few meters across, but weighing less than a gram. The lasers, powered by gigawatts of energy, would fire for only a few minutes, accelerating the sail with photon pressure until it reached its staggering cruise speed. The challenge is immense. Building lasers powerful enough, creating materials that can survive such acceleration without vaporizing, and controlling the direction of countless micro-spacecraft across interstellar distances. Yet the concept itself is rooted in the same fundamental principle demonstrated by LightSail 2, that light can push matter. The allure of solar sailing lies in its purity. It's a propulsion method that doesn't rely on chemical reactions, doesn't pollute, and doesn't run out of fuel. It represents a shift from explosive to elegant engineering, using the quiet, constant energy of the universe itself to move forward. It's propulsion without propellant, motion without mass loss, and endurance limited only by the durability of the sail. Still, it's not without challenges. Solar sails are difficult to deploy. They must unfold flawlessly in the vacuum of space. They're also fragile, vulnerable to micrometeoroids and radiation damage. Moreover, as a spacecraft moves farther from the Sun, the light intensity, and thus the pressure, drops dramatically, following an inverse square law. That means at Jupiter's distance, sunlight is 25 times weaker than near Earth. For true deep space sailing, artificial light sources, like high-powered lasers, become essential. Yet despite these hurdles, the potential of solar sails is transformative. They could revolutionize interplanetary exploration, making missions to the outer planets cheaper and more sustainable. A solar sail could hover indefinitely over the poles of the Sun, map asteroids for decades, or ferry instruments to the Kuiper Belt without worrying about running out of fuel. It's a technology that turns patience into progress, one that trades explosive thrust for the poetry of perpetual motion. If ion propulsion is the quiet hum of the future, solar sails are its silent glide, a whisper of photons guiding humanity outward into the great cosmic ocean. They embody the idea that in space, persistence triumphs over power, and that sometimes the gentlest push is the one that takes you farthest. Next, we'll explore how clever use of gravity itself, not engines or sunlight, has already propelled our spacecraft to the farthest reaches of the solar system, breaking speed records and redefining what's possible in the physics of motion. When we think of speeding up a spacecraft, we tend to picture powerful rockets or advanced engines, machines roaring with thrust and fire. But some of the fastest spacecraft in history didn't get their speed from engines at all. They got it from gravity, the same invisible force that holds planets in orbit and keeps our feet on the ground. Through a brilliant trick of celestial mechanics called a gravity assist or gravitational slingshot, engineers have learned how to steal momentum from planets to accelerate spacecraft across the solar system without spending a drop of extra fuel. It's one of the most ingenious and elegant techniques ever devised in space exploration, a cosmic game of billiards played across millions of kilometers. At its core, a gravity assist uses the motion of a planet around the Sun to give a spacecraft a boost in speed or to change its direction. Here's how it works. When a spacecraft approaches a planet, it falls into that planet's gravitational field, accelerating as it gets closer. If the spacecraft flies behind the planet, in the same direction the planet is orbiting, it can gain some of the planet's orbital energy. To an observer on the planet, it looks as though the spacecraft simply approached and flew away again. But relative to the Sun, it leaves with a higher velocity than it arrived. The planet itself loses an infinitesimally small fraction of its own momentum in the process. But because it's so massive, the change is imperceptible. This exchange of energy might sound like magic, but it's simply physics in action. A perfect interplay of motion and gravity. By planning a precise trajectory, mission designers can use one planet's gravity to reach another, saving enormous amounts of fuel and time. In some cases, a single slingshot maneuver can change a spacecraft's velocity by tens of thousands of kilometers per hour. One of the earliest and most spectacular demonstrations of this technique was NASA's Voyager missions. Launched in 1977, Voyager 1 and Voyager 2 were tasked with exploring the outer planets. But getting there directly would have required far more fuel than any rocket could carry. Instead, mission planners realized that the late 1970s offered a rare celestial alignment, a once-in-176-year event, where Jupiter, Saturn, Uranus, and Neptune would all be positioned perfectly for a grand tour of the outer solar system. By using a series of gravity assists, each Voyager spacecraft could slingshot from one planet to the next, gaining energy at every step. Voyager 2, for example, first flew by Jupiter, using its immense gravity to accelerate and redirect towards Saturn. From there, another slingshot sent it to Uranus, and finally to Neptune. Each encounter was like pushing off one cosmic wall to reach another. Voyager 1, on a slightly different path, used its flybys of Jupiter and Saturn to gain enough speed to escape the solar system entirely. Today, it's the farthest human-made object from Earth, traveling at about 61,000 kilometers per hour, 38,000 miles per hour, relative to the Sun, a velocity it achieved largely thanks to those gravitational boosts. Without gravity assists, neither Voyager would have reached even Saturn, let alone interstellar space. The same principle has powered many of humanity's most ambitious missions. The Cassini spacecraft, which explored Saturn from 2004 to 2017, relied on 4 gravity assists, 2 from Venus, 1 from Earth, and 1 from Jupiter, to gain the energy it needed to reach its distant destination. Without them, Cassini's fuel tanks would have had to be several times larger, making the mission impossible to launch. Similarly, the Galileo spacecraft to Jupiter used 2 Earth flybys and 1 of Venus to build enough momentum for its journey, proving again that gravity could be as useful a tool as any rocket. Even the record-breaking Parker Solar Probe, the fastest spacecraft ever built, owes its incredible speed to gravity assists. But instead of using planetary flybys to gain energy, Parker uses them to lose it. Its goal is to dive closer to the Sun, and because Earth's orbit gives it a large initial sideways velocity, Parker needs to shed orbital energy to fall inward. By flying repeatedly past Venus, Parker effectively hands off some of its momentum to the planet, dropping it into an ever tighter orbit around the Sun. As it descends, the Sun's gravity takes over, pulling it to speeds exceeding 700,000 kilometers per hour, 430,000 miles per hour, faster than any other spacecraft in history. Gravity assists are a kind of cosmic judo, using a planet's massive motion to redirect or accelerate a much smaller object with minimal effort. It's a brilliant exploitation of the natural dance of celestial bodies. Instead of fighting gravity, spacecraft use it, turning the universe itself into an engine. The mathematics behind these maneuvers are intricate, involving precise timing, geometry, and understanding of orbital dynamics. Even a small error in trajectory can mean missing the target planet by millions of kilometers. To execute a successful gravity assist, mission planners must calculate the spacecraft's approach angle, velocity, and timing down to fractions of a second. This makes such maneuvers not only a triumph of physics, but also of human ingenuity and computational precision. Gravity assists don't just increase speed, they can also alter direction in ways impossible with simple engine burns. For example, the Ulysses mission, launched in 1990, used a flyby of Jupiter to bend its trajectory out of the ecliptic plane, the flat disk in which most planets orbit, sending it into a high inclination orbit that allowed it to study the Sun's poles. This maneuver couldn't have been achieved with any reasonable amount of onboard fuel. The beauty of gravity assists lies in their efficiency. Every mission that has ventured beyond Mars, from New Horizons at Pluto to Juno at Jupiter, has relied on this technique in some way. New Horizons, in particular, used a powerful assist from Jupiter in 2007 to gain an extra 14,000 kilometers per hour, cutting years off its journey to Pluto. Without it, the probe might not have reached the dwarf planet until well into the 2020s. In many ways, gravity assists embody humanity's most defining trait in space exploration: the ability to use the forces of nature rather than fight them. They turn massive planets into allies, transforming their gravity, once a prison, into a pathway through the stars. It's a quiet reminder that in the vastness of space, speed doesn't always come from strength or power. Sometimes it comes from grace, precision, and understanding. And as remarkable as these maneuvers are, they highlight a humbling truth. Even with the help of entire planets, our fastest spacecraft are still moving at a crawl compared to the distances between the stars. The next step in our journey takes us to one of those pioneers, the Voyager missions, still racing outward through the dark, carrying humanity's message to the cosmos and showing us just how far and how fast we've come. The Voyager missions are not just spacecraft. They are time capsules, ambassadors, and enduring testaments to humanity's longing to reach beyond the horizon. Launched in 1977, Voyager 1 and Voyager 2 were born in an era when the idea of interstellar travel still belonged squarely in the realm of science fiction. Yet today, nearly half a century later, they are the farthest human-made objects ever to exist, each still racing through the dark beyond our solar system, and still communicating with Earth. They've outlasted the civilizations that built them in many ways. Their launch vehicles are obsolete, their engineers retired, and their technology archaic by modern standards. And yet, they continue to push the boundaries of human presence in space, gliding silently through the interstellar void. Of the two, Voyager 1 holds the title of the fastest and farthest spacecraft ever built. After using gravity assists from both Jupiter and Saturn, Voyager 1 reached an escape velocity so high that it's now moving at approximately 61,000 kilometers per hour, 38,000 miles per hour, relative to the Sun. To put that in perspective, it travels more than 1.6 million kilometers every day, fast enough to circle Earth roughly 40 times in 24 hours. Yet, in the grand scale of the cosmos, that speed is astonishingly slow. Even at 61,000 kilometers per hour, Voyager 1 would take over 75,000 years to reach the nearest star system, Alpha Centauri, located 4.37 light-years away. That's about 25 trillion miles of interstellar distance, a number so vast that even light, the fastest thing in the universe, takes more than 4 years to cross it. For Voyager 1, traveling at what we consider record speed, it's a journey that spans nearly the entire timeline of human civilization. By the time it could theoretically arrive, every mountain on Earth will have eroded, every continent will have shifted, and the memory of our time might exist only in whispers of ancient data. Voyager 1's twin, Voyager 2, took a slightly slower but far more ambitious route, the only spacecraft ever to visit all 4 of the outer planets: Jupiter, Saturn, Uranus, and Neptune. This grand tour was made possible by the rare planetary alignment of the late 1970s, allowing mission planners to use a sequence of gravity assists to sling the probe from one giant world to the next. Voyager 2's speed is a bit lower, cruising at about 55,000 kilometers per hour, 34,000 miles per hour, but its scientific legacy is unmatched. From the discovery of active volcanoes on Jupiter's moon Io to the first close-up views of Uranus's tilted magnetic field and Neptune's supersonic winds. What makes the Voyagers so extraordinary isn't just their destinations, but their endurance. Designed to last just 5 years, both probes have now been operating for nearly 5 decades. In 2012, Voyager 1 crossed the heliopause, the invisible boundary where the solar wind from our Sun gives way to the interstellar medium, officially becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Though still within the Sun's gravitational influence, they are now moving through a region where no spacecraft has ever gone before, sampling the thin gas, magnetic fields, and cosmic rays that flow between the stars. Their data is helping scientists redefine what interstellar space really is. Before Voyager, interstellar was an abstract term. Now, it's a measured reality. The instruments aboard, particularly their plasma detectors, magnetometers, and cosmic ray sensors, are painting a picture of the boundary between the Sun's protective bubble and the wider galaxy. Every bit of data sent back takes more than 22 hours to reach Earth, traveling at the speed of light across more than 24 billion kilometers of emptiness. When those faint signals finally arrive, they carry not just scientific information, but a reminder that even in the most distant corners of space, human curiosity endures. And then there's the Golden Record, perhaps the most poetic artifact ever launched into the cosmos. Each Voyager carries a gold-plated copper disc containing sounds and images chosen to represent the diversity of life and culture on Earth. Greetings in 55 languages, music from Bach to Chuck Berry, the laughter of children, the sound of waves and thunder, and even a message from then US President Jimmy Carter. The Golden Record isn't just a scientific payload, it's a message in a bottle cast into the ocean of the stars. It's our species saying, "We were here. We reached out." In the distant future, long after Earth's surface has changed beyond recognition, the Voyager spacecraft will still be traveling, cold, silent, and intact. Their power supplies, which rely on radioisotope thermoelectric generators, RTGs, are slowly running out. By the mid-2030-50s, their instruments will go dark one by one, and their faint radio signals will fade into the cosmic background. But even after that, the spacecraft themselves will continue to drift through interstellar space, perhaps for billions of years, outlasting the Sun and even the Milky Way's current form. They may be found someday, or never, but in either case, they represent one of humanity's greatest achievements, reaching beyond our solar cradle and sending something of ourselves into eternity. The Voyagers reveal a bittersweet truth about speed and distance. At 61,000 kilometers per hour, they are unimaginably fast by human standards, yet achingly slow on cosmic scales. The nearest star remains tens of thousands of lifetimes away, reminding us that while we've escaped the bounds of our solar system, the universe is still vast beyond comprehension. The gap between us and the stars is not measured merely in kilometers, but in energy, technology, and time. Three barriers that define the limits of our current capabilities. But these little probes, now drifting where no sunlight reaches, are more than just machines. They are symbols of patience, perseverance, and hope. They remind us that progress doesn't always happen in leaps of light years. Sometimes it's a slow, steady drift towards something greater. Voyager 1 and 2 show that even at 61,000 kilometers per hour, we are still at the dawn of our cosmic journey, still infants learning to take our first steps into the galactic ocean. And as we marvel at their long, silent voyage, it's natural to wonder, is there a limit to how fast we can truly go? Could we ever build something that moves faster, not just across planets, but between the stars themselves? To answer that, we must turn to the ultimate boundary of motion, the speed of light, and to the laws of physics that stand as the universe's final speed limit. In the endless, silent expanse of the cosmos, there exists a hard limit, an ultimate barrier that defines what is possible and what forever remains out of reach. It's the speed of light, the cosmic speed limit that governs every movement, every signal, and every interaction in the universe. No object with mass can reach or exceed it. This isn't a technological constraint or an engineering challenge that can be overcome with enough innovation or energy. It's a law of nature, as unbreakable as gravity itself. The speed of light in a vacuum, 299,792 kilometers per second, or roughly 186,282 miles per second, is not just a fast number. It's the fundamental constant that underpins all of modern physics. To grasp how absolute this limit is, consider this. Light can circle Earth more than 7 times in a single second. If you could drive at light speed, you could travel from the Sun to Earth in just over 8 minutes, or across the entire solar system in a few hours. Yet even that astonishing velocity becomes almost insignificant when compared to the vastness of interstellar distances. The nearest star, Alpha Centauri, is over 4.37 light-years away, meaning light itself takes over 4 years to get there. At our current fastest human-made speed, it would take tens of thousands of years. The reason for this immutable limit lies in the foundation of Einstein's theory of relativity. When Albert Einstein published his special theory of relativity in 1905, he redefined the very nature of space, time, and motion. He proposed that the laws of physics are the same for all observers moving at constant speeds relative to one another, and that the speed of light in a vacuum is always constant, no matter how fast you yourself are moving. This idea overturned centuries of Newtonian thought, which treated time and space as fixed, absolute entities. Einstein showed that they are, in fact, woven together into a single fabric, space-time, and that this fabric bends and stretches depending on how fast an object moves. Here's where things get mind-bending. As an object with mass accelerates and approaches the speed of light, several strange but measurable effects begin to occur. First, its mass increases. Not because it's gaining more material, but because, from an external observer's point of view, it becomes harder and harder to accelerate. The energy you put into speeding it up doesn't translate into higher velocity as easily. Instead, that energy increases the object's relativistic mass. This means that the closer you get to light speed, the more energy you need to accelerate even a little bit faster. To actually reach the speed of light would require infinite energy, because the object's mass would also become infinite. This is why, under the laws of relativity, no object with mass can ever reach light speed, and certainly not exceed it. The closer you try to get, the harder the universe resists. It's not a matter of better rockets or more advanced materials. It's a fundamental property of space-time itself. The universe has built-in speed enforcement written into its very structure. Einstein's equations also predict something equally astonishing. Time itself slows down for objects as they move faster. This phenomenon, called time dilation, has been confirmed experimentally many times. For instance, particles called muons, created in Earth's upper atmosphere by cosmic rays, decay in microseconds when stationary. But when they move near light speed, their internal clocks slow down, and they live much longer than they otherwise would. The same principle applies to astronauts aboard high-speed spacecraft or satellites. Their time ticks slightly slower compared to people on Earth, an effect small but measurable, and one that even GPS satellites must account for to maintain precision. At light speed, time would theoretically stop entirely for the traveler. If you could somehow move at that velocity, the journey from one star to another would appear instantaneous, yet to an outside observer, it would still take years. This isn't a paradox. It's a reflection of how differently time and space behave under extreme motion. In Einstein's universe, the faster you move through space, the slower you move through time. To visualize this, imagine space and time as two sides of a coin. When you stand still, all your motion is through time. You age normally. But as you move faster through space, some of that motion shifts from time to space, and time slows down for you. Light, which moves through space at the maximum possible velocity, experiences no passage of time at all. From a photon's perspective, if it could have one, the moment it is emitted and the moment it is absorbed happen simultaneously, no matter the distance in between. This interplay between speed, energy and time forms the essence of relativity, and it's why our dream of faster-than-light travel remains trapped behind a cosmic wall. Every form of propulsion we've ever conceived, from chemical rockets to ion thrusters to nuclear drives, is bound by the same equation. To go faster, you need exponentially more energy. And the closer you get to light speed, the more that energy approaches infinity. No matter how efficient our engines become, as long as we carry mass, the physics of the universe forbids us from reaching the ultimate limit. Yet, even though relativity sets an unbreakable ceiling, it also opens up fascinating possibilities. While we can't exceed the speed of light, relativity allows for phenomena that stretch our imaginations, like time dilation, wormholes, and space-time warping. Concepts that could, in theory, let us travel vast distances without technically breaking the speed limit. But those ideas belong to the realm of advanced and speculative physics, where energy, mass, and geometry of the universe itself intertwine. For now, relativity defines the sandbox we play in. It reminds us that our understanding of motion and time isn't absolute, but deeply intertwined with the universe's structure. Light is not merely fast. It is the standard by which the universe measures all motion. And while it represents an unyielding boundary, it also represents possibility, a challenge that pushes us to rethink what travel, time, and even distance really mean. In the next step of our journey, we'll explore what happens as you approach that barrier, how mass, time, and energy twist under the influence of near light speed travel, and why chasing the speed of light reveals not just the limits of technology, but the limits of reality itself. As we inch closer to the cosmic speed limit, the speed of light, the very rules of motion begin to warp in ways that defy our everyday intuition. Things that once seemed simple, like going twice as fast, become exercises in bending time, stretching energy, and challenging the structure of reality itself. This strange and beautiful territory is governed by relativistic effects, the phenomena that emerge as objects with mass move at significant fractions of light speed. And though we can't yet experience them firsthand, physics allows us to imagine, with stunning precision, what it would feel like to approach that ultimate frontier. The most famous of these effects is time dilation, the slowing down of time for an object as it approaches light speed. It's not just a trick of perspective or perception, it's real, measurable, and has been proven countless times in experiments. According to Einstein's equations, the faster you move, the slower time flows for you relative to someone who is stationary. At a modest 10% of the speed of light, the effect is tiny, barely noticeable. But at 90%, time slows dramatically. For example, if you were traveling at 99.9% of light speed, every second aboard your ship would correspond to roughly 22 seconds for someone on Earth. Push that to 99.9999%, and a single day for you could mean years passing back home. To put it more dramatically, if a human could somehow travel to a distant star at near light speed and then return, they might experience only a few years aboard their ship, while centuries could have passed on Earth. This is the essence of the twin paradox. One twin stays on Earth, while the other travels at relativistic speeds and returns younger than their sibling. It's a mind-bending outcome, but it's been confirmed in real-world physics. High-speed particles like muons, which normally decay in microseconds, live much longer when moving close to light speed. And even the atomic clocks flown on satellites and jets have shown measurable differences in time compared to those on the ground. Time dilation isn't hypothetical. It's a fundamental reality of motion. But time isn't the only thing that changes. As you accelerate closer to light speed, your mass effectively increases from the perspective of an outside observer. In Newtonian physics, mass is constant. 10 kilograms is 10 kilograms, whether it's sitting still or moving. But in Einstein's universe, motion changes everything. The faster an object moves, the more energy it carries, and that energy contributes to its relativistic mass. In simple terms, it becomes harder and harder to accelerate the object as its speed increases. The more energy you put in, the less additional speed you gain. This is why achieving light speed is impossible for anything with mass. At half the speed of light, you've already poured in an immense amount of energy. At 90%, you've invested exponentially more. And as you approach 99.9999%, your energy requirements skyrocket toward infinity. Mathematically, the relationship between speed and energy follows an exponential curve, one that rises so sharply near light speed that no amount of power could ever reach the top. To illustrate this, let's use a simple example. In classical, non-relativistic physics, kinetic energy, the energy of motion, increases with the square of velocity. This means that if you double your speed, you need 4 times as much energy. Triple your speed, and you need 9 times the energy. But in relativity, things are even more extreme, because as you approach the speed of light, you're not just fighting inertia, you're fighting the very fabric of space-time. So while doubling speed at low velocities might require 4 times the energy, doubling it again as you near light speed might require hundreds or thousands of times more. The closer you get, the steeper the climb. For example, if a spacecraft needed 1 unit of energy to reach 10% of the speed of light, it would need roughly 4 units to reach 20%, 20 units for 30%, and so on, 50%, and an absurd 900 units for 95%. To reach 99.9999%, the number shoots toward infinity. In essence, you'd have to convert all the mass in the universe into energy just to accelerate a single object with mass to the speed of light. And even then, you'd fall infinitesimally short. This exponential energy demand is why even our fastest spacecraft, like the Parker Solar Probe or Voyager 1, are crawling compared to light. Parker's record-breaking 700,000 kilometers per hour seems blistering, yet it's only 0.064% of light speed. To reach just 1% of light speed, about 3,000 kilometers per second, would require over 200 times more energy than Parker uses. And to reach 10%, you'd need roughly 20,000 times more. These numbers quickly move from impractical to impossible with current or even near-future technology. But what's truly fascinating and counterintuitive is how relativity changes our understanding of motion itself. From the traveler's perspective, no matter how fast they go, they never feel heavier, nor do they feel time slowing down. Their ship behaves normally. It's only from the outside, from the viewpoint of someone stationary, that these effects become visible. To the traveler, space appears to contract in the direction of motion, a phenomenon known as length contraction. Distances ahead seem shorter, compressed. This means that even though the traveler cannot exceed light speed, they could, in theory, reach distant stars more quickly in their own frame of reference because space itself has shrunk around them. Imagine a spacecraft traveling to a star 10 light-years away at 99.99% of light speed. To observers on Earth, the journey would take roughly 10 years. But to the crew aboard, time dilation and length contraction would make it seem much shorter, perhaps only a few months or a year. For them, the trip would feel manageable. For Earth, decades would pass. This strange interplay between time and space makes relativity one of the most awe-inspiring and limiting principles in physics. The enormous energy requirements of near light speed travel aren't just numbers on paper, they define the boundaries of what we can do. Every gram of fuel, every burst of thrust, every watt of power must contend with relativity's steep curve. It's a cosmic economy that punishes brute force and rewards creativity. We can't simply burn our way to the stars. We must outthink the universe's laws if we ever hope to travel beyond them. And that's exactly where the next generation of propulsion concepts enters the picture. From nuclear fusion drives to antimatter propulsion and even the mind-bending warp drive, scientists and dreamers alike are searching for ways to skirt, bend, or work with relativity's limits instead of trying to break them. Because if infinite energy is the cost of light speed, then the only real path forward may lie not in moving faster through space, but in changing space itself. As we stand at the edge of what our current technology can achieve, it becomes clear that chemical rockets, magnificent though they are, have taken us as far as they can go. To reach beyond Mars, beyond the outer planets, and perhaps one day to other stars, we'll need engines that go far beyond mere combustion. That's where futuristic propulsion concepts come in. Ideas that tap into the deepest and most powerful forces of nature: nuclear reactions, fusion energy, and even matter-antimatter annihilation. These technologies are not just evolutions of current systems, they're revolutions in how we think about movement through space, potentially allowing us to travel orders of magnitude faster than ever before. Let's start with something relatively near-term: the nuclear thermal rocket, NTR. This concept isn't science fiction. It's been researched and tested since the 1960s during NASA's NERVA program, Nuclear Engine for Rocket Vehicle Application. A nuclear thermal rocket replaces the chemical combustion chamber of a traditional rocket with a nuclear reactor. Instead of burning fuel, it uses fission, the splitting of atomic nuclei, to heat a lightweight propellant like liquid hydrogen to extreme temperatures. The hot hydrogen expands and shoots out through a nozzle, producing thrust. Why is this revolutionary? Because fission reactions are millions of times more energy dense than chemical ones. That means a nuclear thermal rocket could achieve specific impulses, the measure of efficiency, roughly twice as high as chemical rockets, reaching 900 to 1,000 seconds compared to 450 for the best chemical engines. That might not sound like much, but in spaceflight, doubling efficiency can mean cutting travel times to Mars by half or carrying far heavier payloads for the same fuel. NASA and DARPA are actively working on new designs under the DRACO program, which aims to test a nuclear thermal engine in orbit by the early 2030s. If successful, NTRS could become the workhorses of interplanetary travel, fast, powerful, and reusable. But even nuclear thermal propulsion is just the beginning. The next step in the hierarchy of advanced propulsion is nuclear fusion, the same process that powers the Sun. While fission splits atoms, fusion combines light atomic nuclei like hydrogen isotopes into heavier ones like helium, releasing tremendous energy in the process. The potential here is staggering. Fusion reactions release about 4 million times more energy per kilogram than chemical fuel and about 4 times more than nuclear fission. If we could harness it efficiently, fusion propulsion could propel spacecraft to a few percent of the speed of light, fast enough to make interstellar exploration conceivable within human timescales. One of the most famous concepts in this category is the Daedalus project, proposed in the 1970s by the British Interplanetary Society. It envisioned an uncrewed interstellar probe powered by inertial confinement fusion, using tiny pellets of deuterium and helium, 3 isotopes of hydrogen and helium ignited by electron beams. The energy released would create plasma exhaust at incredible speeds, propelling the craft to 12% of light speed, enough to reach the nearest stars in less than 50 years. More recent studies, like Project Icarus and NASA's fusion-driven rocket, have built on those ideas with updated materials and technology, hoping to one day make fusion propulsion viable. In a working fusion rocket, you could envision the spacecraft carrying a magnetic confinement system, a sort of miniaturized fusion reactor that superheats plasma and ejects it through a magnetic nozzle. The challenge, of course, is that fusion itself is extraordinarily difficult to control. Even on Earth, despite decades of research, sustained fusion reactions have only just begun to show promise in experimental reactors like ITER and NIF. Still, if fusion can be mastered, it could reduce travel time to Mars to a few weeks, to Jupiter in a matter of months, and even to nearby stars within a century. Then there's the most exotic, and potentially most powerful, of them all, antimatter propulsion. In the strange world of particle physics, antimatter is the mirror twin of regular matter. When a particle of matter meets its antimatter counterpart, they annihilate completely, converting their entire mass into pure energy according to Einstein's famous equation, E equals mc squared. The energy density of this reaction is almost incomprehensible. 1 gram of antimatter reacting with 1 gram of matter releases the same energy as about 43 kilotons of TNT, roughly the yield of a nuclear bomb. That's the energy equivalent of millions of chemical rocket stages packed into something that could fit in your hand. If we could build an antimatter engine, it would be the ultimate propulsion system. Theoretically, such a spacecraft could achieve speeds up to 50% or even 80% of light speed, depending on efficiency and design. Concepts like antimatter-catalyzed microfusion propose using tiny amounts of antimatter to trigger controlled fusion reactions, combining the energy density of antimatter with the manageability of fusion. NASA's Breakthrough Propulsion Physics program and independent physicists like Robert Forward have studied how such systems might work, envisioning ships powered by magnetic nozzles that channel high-energy plasma from annihilation reactions to produce thrust. The challenges, however, are colossal. Antimatter is incredibly rare in the universe and must be created artificially in particle accelerators. at a cost of billions of dollars per microgram. Storing it safely is even harder, since it annihilates on contact with normal matter. That means it would have to be held in place by sophisticated magnetic containment fields, with any failure resulting in catastrophic destruction. Yet despite these challenges, the physics is sound. Antimatter engines, if ever built, would represent the pinnacle of energy efficiency, converting 100% of mass into thrust energy. No chemical or even nuclear system can come close. Beyond these, scientists have dreamed up other radical concepts, such as Bussard ramjets, enormous fusion-powered ships that scoop up hydrogen from interstellar space as fuel, and beam-powered propulsion, where lasers or microwaves from Earth or orbit provide energy to distant spacecraft. Each of these pushes the boundaries of what's possible, exploring ways to overcome the tyranny of carrying one's own fuel. What unites all these ideas, from nuclear thermal to fusion to antimatter, is the quest for efficiency, endurance, and speed. They all aim to solve the same fundamental problem: how to produce continuous, high-energy propulsion without requiring mountains of fuel. Where chemical rockets burn brightly and die quickly, these future engines could, in theory, burn softly but steadily, accelerating for months or even years, until their velocities reach unimaginable levels. If chemical propulsion is our candle, then nuclear and antimatter propulsion are our suns, gateways to a future where humanity can traverse not just planets, but the distances between stars. Yet even these incredible concepts, with all their power, still bow to one fundamental rule. No matter how fast they go, they cannot exceed the speed of light. That unbreakable boundary has led scientists to wonder if there's another way. Not to move faster through space, but to move space itself. And that's where we arrive at one of the most mind-bending ideas in all of physics: the Alcubierre warp drive, a concept that could, at least theoretically, make interstellar travel faster than light without ever breaking relativity's laws. If there's one idea in physics that captures both our imagination and our longing for the stars, it's the warp drive, a concept that seems torn straight from the pages of science fiction, yet is grounded, at least in theory, in real physics. The most famous version of this idea is the Alcubierre warp drive, proposed in 1994 by Mexican physicist Miguel Alcubierre, who found a fascinating loophole in Einstein's equations of general relativity. According to his mathematics, faster-than-light travel might be possible, not by breaking the cosmic speed limit, but by bending space itself. To understand the Alcubierre concept, we first need to recall what Einstein taught us: that space and time are not rigid, separate entities, but part of a single, flexible fabric called space-time. Massive objects, like planets and stars, warp this fabric. That's what we perceive as gravity. Alcubierre realized that if space could be curved by mass, maybe it could also be manipulated in other ways, perhaps even engineered to move a spacecraft faster than light without the ship itself ever exceeding light speed within its local bubble of space-time. Here's how it would work. Instead of propelling a spacecraft through space, the Alcubierre drive would manipulate the space around it. The idea involves creating a warp bubble, a region of space that contracts in front of the spacecraft and expands behind it. Inside this bubble, the spacecraft would sit in a kind of flat, unchanging region of space-time, effectively at rest relative to its local environment. But because the space behind it is expanding and the space ahead of it is contracting, the entire bubble could move through the universe faster than light relative to an outside observer. To visualize this, imagine placing a marble on a rubber sheet. Normally, to move the marble from one side to the other, you'd have to roll it along the surface. But with the warp drive, you'd instead stretch and compress the rubber sheet itself, moving the marble effortlessly from one side to the other, while the marble itself barely moves. This is the essence of the warp bubble, a ship that doesn't travel through space, but rides a wave of space-time distortion. In principle, this approach avoids violating Einstein's rule that nothing can move through space faster than light, because the ship itself never actually breaks that limit. Locally, inside the bubble, everything obeys the laws of physics. It's the space itself, which isn't restricted by the speed of light, that does the moving. This theoretical framework allows for effective, faster-than-light travel, or superluminal motion, without violating relativity. However, as elegant as Alcubierre's mathematics may be, the practical challenges are almost insurmountable, at least with our current understanding of physics. The biggest problem is energy. To warp space-time in this way, you'd need to manipulate unimaginable amounts of energy, possibly negative energy or exotic matter with properties unlike anything we've ever observed. Negative energy isn't something you can find in nature. It's a hypothetical concept that arises from certain quantum effects, like the Casimir effect, where tiny amounts of negative energy density have been observed between closely spaced plates. But the amount required to create even a small warp bubble would be astronomical. Initial estimates suggested that a warp drive capable of moving a modest-sized spacecraft would require more energy than the entire mass of the observable universe converted into energy. Clearly an impossible figure. Later refinements of the theory by physicists like Harold Sonny White at NASA's Eagle Works laboratories have proposed more energy-efficient versions, reducing the requirements by many orders of magnitude. Even so, the energy needed is still far beyond anything humanity can currently produce or contain, roughly equivalent to the total output of our Sun over many years. There's also the issue of stability. The mathematics behind the warp bubble suggests that regions of extreme gravitational distortion would form at the edges, potentially releasing massive amounts of radiation and energy. Any object caught in or near that boundary could be vaporized instantly. Worse still, because the bubble isolates its interior from the rest of space-time, the spacecraft inside might not be able to communicate or control the bubble once it's in motion. Starting it, steering it, or stopping it could all be impossible once underway. And then comes a deeper philosophical challenge: causality. In relativity, cause and effect are linked by the finite speed of light. But a warp bubble traveling faster than light would, in theory, allow effects to precede their causes, creating paradoxes where events influence their own past. It's the kind of puzzle that makes physicists both fascinated and uneasy, because it threatens the logical structure of the universe as we understand it. Despite all these hurdles, the Alcubierre drive remains one of the most intriguing theoretical ideas ever proposed. It doesn't rely on breaking physics, it relies on pushing physics to its limits. And that's why scientists continue to study it, not as a practical blueprint for interstellar ships, not yet anyway, but as a thought experiment that reveals just how flexible Einstein's equations truly are. In recent years, a handful of researchers have taken small steps toward exploring whether any aspect of the warp concept could be experimentally tested. In 2021, a team led by Harold White claimed to have found a micro-scale warp bubble while modeling quantum vacuum structures. Though this was not a working drive, it hinted that certain space-time geometries resembling Alcubierre's solution might occur naturally under quantum conditions. It's far from proof, but it keeps the dream alive. That one day we might learn to shape space-time the way a sailor shapes the wind. For now, the Alcubierre warp drive remains purely theoretical, a symbol of what could one day be possible if our understanding of physics deepens dramatically. It sits at the crossroads of science and imagination, reminding us that the boundaries between them are often thinner than we think. And while warp drives may be the distant dream of tomorrow, there are more realistic steps we can take in the near future. Technologies already under development that could make us faster, more efficient, and capable of reaching the outer planets and beyond within our lifetimes. These are the realistic future goals of space travel. Propulsion systems that won't bend space-time, but will push humanity farther than ever before. While warp drives and exotic space-time manipulation remain theoretical dreams shimmering on the horizon of possibility, the realistic future of space travel will be built not on fantasy, but on the relentless evolution of physics and engineering. Over the next few decades, the question isn't whether we'll go faster, it's how much faster we can go with the technology within our reach. And though the cosmic speed limit of light, 300,000 kilometers per second, will remain insurmountable, new propulsion systems may one day propel humanity to a respectable fraction of that speed, perhaps 1% to 10% of light speed. That may not sound like much, but in the realm of interstellar distances, it would be revolutionary. Let's begin with what might be achievable in the next half-century: fusion propulsion. Fusion remains the crown jewel of future energy sources, both for Earth and space. While we're still in the experimental phase of developing sustained, controlled fusion reactions here on Earth, several space agencies and private research initiatives are already exploring how that energy could one day power spacecraft. Fusion propulsion would use the same principle that powers the Sun, fusing light atomic nuclei such as deuterium and tritium into heavier elements, releasing immense amounts of energy. Unlike chemical or fission reactions, fusion converts a small portion of mass directly into energy, according to Einstein's E=mc². The result? A fuel that's millions of times more efficient than chemical propellants, producing enormous thrust without the radioactive waste associated with fission. In practical terms, fusion engines could potentially accelerate spacecraft to speeds of tens of thousands of kilometers per second, roughly 1% to 5% of light speed. This would shrink travel times across the solar system from years to mere weeks or months. A fusion-powered ship could reach Mars in about 2 weeks, Jupiter in a month, or Pluto in a few months. For interstellar travel, 1% of light speed would mean reaching Proxima Centauri, our nearest stellar neighbor, in about 400 years, still far beyond a single human lifetime, but a blink in cosmic terms. Several real-world designs have been proposed to bring this dream closer. The Daedalus and Icarus concepts, developed by the British Interplanetary Society, envision massive fusion-powered probes using helium-3, a rare isotope believed to be abundant on the Moon and in the atmospheres of gas giants. Project Daedalus, designed in the 1970s, calculated that a 2-stage fusion spacecraft could reach 12% of light speed, or roughly 36,000 kilometers per second, by detonating thousands of small fusion pellets behind a magnetic nozzle. A journey to nearby stars like Barnard's star could take just 50 years, long enough for a robotic probe to reach another solar system within a human lifetime. More recently, organizations like NASA, Helicity Space, and the Fusion-Driven Rocket Project have explored using magnetized plasma confinement to create compact, efficient fusion thrusters. These would operate like miniature suns, continuously generating thrust by heating plasma to millions of degrees and directing it magnetically. If such systems could be built, they would fundamentally redefine deep space exploration, enabling constant acceleration over long durations rather than short bursts of chemical thrust. But even more ambitious is the concept of laser or beam propulsion, where the energy to move a spacecraft doesn't come from onboard fuel at all. Instead, powerful lasers or microwaves, stationed on Earth, the Moon, or in orbit, would beam concentrated energy toward a spacecraft equipped with reflective sails or absorptive plates. The Breakthrough Starshot initiative is the most famous of these efforts. Proposed in 2016, it aims to send a fleet of ultralight nanocraft, each weighing only a few grams, propelled by a 100 gigawatt laser array on Earth. These miniature probes, attached to sails a few meters wide, could be accelerated to 20% of light speed, about 60,000 kilometers per second, within just a few minutes of laser firing. At that speed, these probes could reach Alpha Centauri in just over 20 years, allowing humans to send the first interstellar mission within a single generation. The data they transmit back, even if it takes 4 years to reach us, would represent humanity's first glimpse of another star system up close. Of course, this approach only works for tiny, unmanned probes. Scaling it up to human-sized ships would require energy sources far beyond our current capabilities. Still, the technology could open a new era of rapid robotic exploration throughout the solar system and beyond. Even achieving 1% of light speed, though, would be transformative. A spacecraft traveling at that velocity, around 3,000 kilometers per second, could cross the distance between Earth and the Moon in under 2 minutes, reach Mars in a day, and traverse the entire solar system in under a week. The implications for exploration, communication, and colonization would be staggering. Interplanetary missions would no longer be months-long endurance tests, but short hops across the neighborhood. Entire economies could develop around regular cargo and passenger traffic between planets. Humanity's sphere of influence could expand from one fragile world to an entire system of worlds. Yet, the gap between 1% and 10% of light speed is vast. Each step upward demands exponentially more energy and engineering sophistication. At 10% of light speed, or 30,000 kilometers per second, travel to the nearest star would still take 43 years, long enough for a probe, but still beyond the reach of a human crew's lifespan. Reaching those velocities would likely require hybrid systems, perhaps a combination of fusion drives, antimatter catalysis, and laser acceleration, along with revolutionary breakthroughs in materials science to withstand the heat and radiation of sustained high-velocity flight. Still, even these slow interstellar speeds would mark the dawn of a new age, humanity's transition from a planetary to an interstellar species. The first ships capable of traveling between stars might be generation ships, massive vessels designed to sustain self-contained civilizations over centuries-long journeys. Alternatively, AI-controlled robotic probes could scout the galaxy, carrying digital seeds of human knowledge, or even consciousness, to other worlds. The beauty of this vision lies in its balance between reality and wonder. Unlike warp drives or wormholes, fusion and laser propulsion don't demand breaking the laws of physics, only bending them to our advantage. These are the technologies that could actually exist within a century, given sustained research and international effort. They won't make interstellar travel easy, but they'll make it possible. And that's enough to change everything. If we achieve 1% of light speed, we'll open the gateway to the stars. At 10%, we'll become truly cosmic beings. And every step toward those milestones, each improvement in propulsion efficiency, energy production, and material endurance, will ripple outward, transforming not only how we explore the universe, but how we understand our place within it. Yet before we dream too far beyond the stars, we must remember that speed matters not just for ambition, but for practicality. How quickly can we travel right now to the worlds in our own solar system? How long does it take us, even with today's technology, to reach the Moon, Mars, or Jupiter? And how would those times shrink as our engines evolve? That's where we turn next, the real-world travel times that define our current reach, and how the next generation of propulsion will change what's within our grasp. In the vast, silent theatre of our solar system, distance is the first and greatest adversary of exploration. The worlds that glitter in our night sky may look close enough to touch, but in truth, they are unimaginably far. Every voyage into space is a test of patience and endurance as much as it is of technology. With our current propulsion systems, primarily chemical rockets, We have reached the Moon, sent probes to every major planet, and even launched a few machines beyond the Sun's grasp. Yet, in cosmic terms, we've barely taken our first steps. Let's start close to home. The Moon, our nearest celestial neighbor, lies about 384,000 kilometers, 238,000 miles, away. That's a distance light covers in just 1.3 seconds. But for human spacecraft, it's a 3-day journey. During the Apollo missions of the late 1960s and early 1970s, astronauts rode atop the mighty Saturn V rocket, which hurled them toward the Moon at speeds around 39,000 kilometers per hour, 24,000 miles per hour. At that pace, Apollo 11 took about 76 hours to reach lunar orbit before descending to the surface. Even today, that's roughly the benchmark for a crewed lunar trip. If humanity's new generation of rockets, NASA's SLS or SpaceX's Starship, fulfills their promise, travel time to the Moon could shrink slightly, perhaps to 2 or 2.5 days, depending on trajectory and efficiency. Move farther out, and the distances grow exponentially. Mars, our most immediate interplanetary goal, orbits an average of 225 million kilometers, 140 million miles, from Earth, though the exact distance varies depending on alignment. When Earth and Mars are on the same side of the Sun, the point called opposition, the journey is at its shortest. Using current propulsion systems, such as the ones that carried NASA's Perseverance rover or InSight lander, the trip takes between 6 and 9 months. The spacecraft accelerate for only a short period at launch and then coast most of the way along an orbital trajectory known as a Hohmann transfer orbit, which is the most fuel-efficient but not the fastest route. A faster chemical journey to Mars could theoretically be done in about 3 to 4 months, but that would require carrying significantly more propellant, which dramatically increases launch mass and cost. With next-generation propulsion systems like nuclear thermal rockets, NTRS, or fusion engines, the picture changes drastically. An NTR could potentially reduce travel time to Mars to 6 to 8 weeks, while a fusion-powered spacecraft, constantly accelerating for half the trip and decelerating for the other half, could make the same journey in as little as 2 weeks. Such speed would transform human missions from year-long expeditions into practical, sustainable journeys, reducing radiation exposure and making regular Mars travel feasible. Now consider Jupiter, the giant of our solar system, orbiting an average of 778 million kilometers, 484 million miles, from the Sun. A spacecraft leaving Earth today, propelled by traditional chemical rockets, takes 5 to 6 years to reach it. The Galileo mission launched in 1989 and arrived in 1995, after using multiple gravity assists from Venus and Earth to gain the necessary velocity. Similarly, Juno, launched in 2011, didn't reach Jupiter until 2016. Even the fastest route ever to Jupiter, taken by New Horizons on its way to Pluto, still required just over 13 months, and that was a lightweight probe optimized for speed. If we had nuclear or fusion propulsion, the timeframes would collapse dramatically. A fusion-powered ship could reach Jupiter in just a few weeks. Ion propulsion or advanced plasma thrusters could shave years off unmanned missions, allowing for rapid resupply or human exploration of the outer planets, something currently impossible with chemical propulsion due to both time and fuel constraints. Saturn, nearly 1.4 billion kilometers, 870 million miles away, presents an even steeper challenge. The Cassini mission took almost 7 years to get there after multiple planetary flybys, but with next-generation engines, that could fall to a few months. Imagine sending a scientific probe to Saturn and receiving data in the same year, instead of waiting nearly a decade for arrival. The outer planets, Uranus, Neptune, and the dwarf planet Pluto, would become reachable in years instead of generations. A probe powered by fusion or antimatter could reach Neptune, currently a 12-year journey, in less than a single Earth year. Even more compelling is how faster propulsion changes not only travel time, but also mission design. Today's space missions must be meticulously planned years in advance, with launch windows tied to precise planetary alignments. Missing that window can delay a mission for years. Faster engines would remove that limitation entirely. Spacecraft could leave any time, on flexible trajectories, and still arrive quickly. Space travel would shift from a rare, time-sensitive event to a routine logistical operation. To illustrate just how transformative this would be, consider this. Moon, from 3 days to a few hours. Mars, from 6 to 9 months to 2 to 4 weeks. Jupiter, from 5 years to 1 to 2 months. Saturn, from 7 years to 3 months. Neptune/Pluto, from over a decade to less than a year. These changes don't just alter exploration, they alter civilization. A human presence on Mars would no longer be a one-time event, but a continuous exchange of people, materials, and knowledge. Colonies on the Moon or Mars could receive supplies on a weekly or monthly basis instead of annually. Outer planet missions could be conducted in real time, with scientists commanding rovers and drones almost directly instead of waiting hours or days for signals to travel back and forth. Perhaps most intriguingly, faster travel redefines the psychological distance between worlds. The Moon could become as accessible as an overseas flight today. Mars could become the next continent, far but familiar. Humanity would, for the first time, be able to think of itself as a multi-world species, connected by travel times measured not in years, but in days. Of course, even with the most optimistic projections, interstellar travel remains another leap entirely. At 1% of the speed of light, about 3,000 kilometers per second, the nearest star system, Alpha Centauri, would still be over 400 years away. At 10%, that journey shortens to just over 4 decades, theoretically reachable by a single generation, though still unimaginably challenging. Yet every technological milestone we reach within our solar system, from faster travel to better energy efficiency, brings us closer to that interstellar threshold. Speed, then, is not just a measure of motion, it's a measure of freedom. The faster we can move between worlds, the less isolated we become, and the more the solar system begins to feel like home. With each leap in propulsion technology, we shrink the vastness of space, drawing planets closer in both time and imagination. And as our engines grow more powerful, we will eventually face not only the challenge of moving faster, but of keeping ourselves and our machines safe as we do so. Because traveling faster in space isn't just about propulsion, it's also about survival, about shielding fragile human lives and delicate machines from the radiation, debris, and energy that come with ever greater velocity. That's the next frontier in our journey, how to protect humanity as we push the limits of speed. Going faster in space isn't only a question of propulsion, it's a question of survival. Every increase in speed multiplies the danger. Space isn't empty, it's filled with radiation, dust, and microscopic debris traveling at tens of thousands of kilometers per hour. At those velocities, even a grain of sand becomes a lethal projectile. For humans and spacecraft alike, the faster we go, the harsher the environment becomes. Radiation is the first and most relentless threat. Once beyond Earth's magnetic shield, astronauts are bombarded by solar radiation and cosmic rays, high-energy particles that can slice through cells, damage DNA, and increase cancer risk. On slow missions, exposure builds gradually. On faster ones, shielding must withstand even more intense particle impacts. Traditional materials like aluminum aren't enough. Future spacecraft may require hydrogen-rich polymers, magnetic fields, or active plasma shields to deflect radiation. Some designs even propose using the ship's fuel or water as a protective barrier around the crew habitat. Then there's the problem of micrometeoroids, tiny dust grains scattered across the solar system. At high speeds, their kinetic energy is devastating. A 1 millimeter particle striking a ship moving at just 1% of light speed would hit with the force of a hand grenade. At 10% of light speed, it would be equivalent to a large bomb. To survive such impacts, spacecraft would need multi-layered shielding, self-healing materials, or electromagnetic deflection fields to vaporize incoming debris before contact. Even the smallest miscalculation could tear a hull apart. And as velocity climbs, heat and stress become enormous challenges. High-speed particles generate radiation and plasma sheaths around the ship. Every collision produces heat, static charge, and electromagnetic interference. Maintaining control systems and communications in such conditions will demand revolutionary materials and real-time adaptive shielding, far beyond anything used on today's rockets. For humans, there's also the physiological toll. Prolonged exposure to acceleration forces, radiation, and isolation can strain the body and mind. Artificial gravity, advanced life support systems, and radiation-hardened habitats will all be essential for long-duration, high-speed missions. In short, going faster isn't just about better engines. It's about outsmarting physics itself to keep fragile human life safe in a universe that resists our every attempt to move through it. The next generation of spacecraft will be as much about armor and resilience as about thrust and speed. Next, we'll look at what's actually being developed right now, the projects and programs that are turning these challenges into the next steps of real exploration. Right now, as humanity stands at the threshold of a new space age, a wave of ambitious projects, both governmental and private, are transforming what once seemed like distant dreams into tangible plans. These efforts aren't just about exploring space, they're about building a sustainable, long-term presence beyond Earth and developing the propulsion systems that will carry us farther and faster than ever before. At the forefront is NASA's Artemis program, the most significant step in human space exploration since Apollo. Artemis isn't just a return to the Moon, it's a rehearsal for going deeper into space. The missions will establish the Artemis base camp on the lunar surface and the Gateway, a small space station orbiting the Moon that will serve as a launch point for future missions to Mars. To make this possible, NASA is leveraging the Space Launch System, SLS, the most powerful rocket ever built since the Saturn V, capable of sending over 95 tons to orbit. Each Artemis mission will test new systems for deep space survival, radiation shielding, autonomous navigation, and long-term life support, all essential for future high-speed journeys to Mars and beyond. Meanwhile, Europe's ESA, European Space Agency, is laying the groundwork for the next leap in propulsion. ESA's nuclear propulsion research is focused on developing both nuclear thermal and nuclear electric propulsion systems, engines that could drastically reduce travel times across the solar system. By harnessing nuclear energy for sustained thrust, these systems could make months-long missions to Mars possible, not once per decade, but as part of a continuous interplanetary network. Their studies on fission reactors in orbit and modular propulsion units are setting the stage for Europe's contribution to future deep space logistics. In the United States, the Defense Advanced Research Projects Agency, DARPA, is pushing forward with Project DRACO, the demonstration rocket for agile cislunar operations. This program aims to test a nuclear thermal rocket in space by the early 2030s, using a compact reactor to heat hydrogen propellant and produce incredibly efficient thrust. Unlike traditional rockets that burn chemical fuel, DRACO's nuclear engine could operate continuously for long periods, enabling rapid maneuvering in cislunar space, the area between Earth and the Moon, and opening the door for future Mars missions. DRACO's success would mark a major turning point, proving that nuclear propulsion isn't just theory, but a deployable, game-changing technology. But government programs aren't leading the charge alone. Private companies are accelerating the new era of space travel with bold, disruptive innovation. SpaceX's Starship, for instance, is designed to be fully reusable and capable of carrying up to 150 tons of cargo or 100 passengers into space. With its Raptor engines powered by methane and liquid oxygen, Starship aims to slash the cost of spaceflight while offering interplanetary range. Elon Musk's long-term vision is to establish a self-sustaining city on Mars, and Starship's design reflects that goal: modular, powerful, and capable of refueling in orbit. When fully operational, it could make round trips between Earth and Mars routine, with flight times measured in months rather than years. Blue Origin, founded by Jeff Bezos, is pursuing a complementary vision, focusing on building the infrastructure for permanent space habitation. Through projects like the New Glenn rocket and the long-term goal of Blue Moon lunar landers, the company aims to establish a sustainable supply chain between Earth and space. Their philosophy centers on moving heavy industry off Earth, preserving the planet while humans live and work in space. Beyond that, Blue Origin has hinted at nuclear propulsion development and reusable lunar transport systems that could support both Artemis and commercial missions. Together, these efforts, public and private, are converging into something greater than any single mission: a global movement toward a spacefaring civilization. The Artemis missions will test our ability to live and work beyond Earth's orbit. ESA's nuclear research and DARPA's DRACO will lay the foundations for faster, longer-range propulsion. And SpaceX and Blue Origin are building the vehicles that will make space travel affordable, repeatable, and scalable. We're witnessing the early stages of humanity's transition from exploration to expansion, from visiting space to inhabiting it. Each rocket launch, each engine test, and each lunar landing is a rehearsal for a future where journeys to other planets, or even other stars, are no longer the stuff of science fiction. And as this new chapter unfolds, one truth stands out. Speed isn't just about getting somewhere faster, it's about expanding what's possible. Because the faster we can move through the cosmos, the more our vision of the future begins to resemble something limitless. Next, we'll close this journey with a reflection on that vision. A look toward what comes after all of this, when the question isn't, how fast can we travel right now, but how far can we go next? In the vastness of the cosmos, our greatest achievements still amount to baby steps. From the Apollo astronauts who blazed toward the Moon, to the Parker solar probe racing through the Sun's fire, every mission has carried us a little farther from home and a little closer to the stars. We are, by cosmic standards, still crawling, our ships whispering across the darkness while light itself streaks beyond our reach. Yet each new discovery, each breakthrough in propulsion or power, is a promise that one day we'll go faster, farther, and braver than ever before. The universe is waiting, silent, endless, and full of possibility. The only question left is, how fast will we go next? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.